Today, I'll talk about an introduction to NLP4L, NLP4 Lucene. Lucene is the most successful search software in the world. The goal of NLP4L is to improve Lucene users' search experience by the assistance of NLP technique. There is a famous problem in IR field, the trade-off problem between precision and recall. They are incompatible. I'll mainly talk about how we try to solve this problem in our project. Before going into my talk, let me briefly introduce myself. My name is Koji Sekiguchi. I'm the founder and CEO of RONDHUIT, a search company based in Tokyo. We deliver our services regarding Lucene and Solr, especially Solr, to our customers. I'm a committer of Apache Lucene and Solr, so I'm a search guy. As for my experience of Scala, I'm not an expert. I've been working on it for just a few months. This is the outline of my talk. First off, I'll briefly go over NLP4L. Then I explain how NLP technique can improve user search experience. Because some of NLP techniques help improve search result, it is important to understand this in order for you to figure out what the goal of NLP4L is and why. Next, I'll explain how to count the number of words in Lucene index. It might sound a bit boring to you, but it's the first step for calculating probability, such as language model or hidden Markov model. I'll talk about these models shortly. Then, I'll show you an interesting application, Transliteration. NLP4L provides it as an example script. I'll show you the demo if we have time. Then, I'll share our future plans for this project. So, what's NLP4L? Again, it stands for NLP2 for Lucene. It's an open source project with Apache license written in Scala. Our goal is to improve Lucene user search experience using NLP technique. The most distinct characteristics of our project is that it uses Lucene index as a corpus database. Instead of using text data directly, NLP4L lets users put their text data into Lucene index. Once the data is in, words appearing in corpus are settled in Lucene index. Trying to count the number of words, NLP4L reads Lucene index instead of original text data. There are some other aspects in our project, though. I'll show you Transliteration program later. As it uses hidden Markov model, and when calculating probabilities for HMM, it uses Lucene index to get the word count. In order to better understand later slides, let me quickly explain what Lucene is. Lucene is a search engine library written in Java. It's Apache licensed and open source with a very active community. Lucene has a variety of functions for information retrieval, including indexing, searching, analyzing, parsing, dictionaries, etc. But I want to focus only on this picture. Lucene makes an inverted index so you can search text documents. Here, we have 3 documents that we want to search. So we index them to Lucene, and Lucene in turn makes an inverted index from them. The index has a list of words appearing in all documents. Each word has posting list, that is a list of document numbers of ones that have the corresponding words in them. Once Lucene has the index, users can execute queries. For example, when you post a query Apple, Lucene finds it in the index quickly and returns the document numbers 1 and 3 that includes the query word. Next, I'll explain how NLP improves such experience. I think it's important to know how NLP technologies can improve users' experience when they search. By knowing it, we understand why NLP4L provides functions that are being implemented now. I'm going to illustrate 2 evaluation measures that are very popular in IR field, the precision and the recall. They are often used in the field of machine learning or NLP. So you may be familiar with these measures, but let me explain them quickly. Here, we have a rectangle, and I'm going to draw a Venn diagram. This rectangle represents a universal set. This set is a universal set of documents to be searched by the search engine users. When the search engine has 1 million documents in its index, the size of this rectangle is also 1 million. Here, you post your query, let's say query X, to the search engine. When you do that, you have your expectation. You have a set of documents in your mind that you want the search engine return for you. Let's call it a target set, because it's the target for search engine. If the search engine returns a set like the pink circle here, the user is happy and satisfied by the result. But in reality, the search engine cannot fully satisfy you, though it could satisfy your expectation partially. So here is a blue circle in the rectangle like this. It covers a part of the target set. As a result, the inside of the rectangle would be separated into 4 sections. 4 sections are composed of the combination of positive, negative, and true, false. The result set is considered in positive as the search engine thinks that the set of documents in the blue circle satisfy your expectation. And the outside of the result set is considered in negative, as the search engine thinks that the set of documents that are not there are a set of documents that are out of blue circle don't satisfy your expectation. They are partially correct and partially incorrect. From the user's point of view, they are labeled as true or false. Let's look at true area. True area has 2 sections, true positive and true negative. True means the right answer. For example, true positive is the area where a set of documents that are returned by the search engine and are wanted by you. And true negative is the area where a set of documents that are not returned by the search engine and that are not wanted by you. On the other hand, false area can be considered in wrong answers. For example, false positive is the area where a set of documents that are returned by the search engine but are not wanted by you. And false negative is the area where a set of documents that are not returned by the search engine but are really wanted by you. Here, we have all parameters that are going to be used in our evaluation measures. They are precision and recall. They are very popular, as you might have heard of them. The precision is a measure used when you want to represent the precision of the search engine you are using. To calculate the precision, you use the first formula, TP over TP plus FP, or instead, TP divided by the size of the result set, the blue circle. For example, if you make a query and the search engine returns 100 documents, but you find only 3 documents that satisfy your expectation, then the precision is 3%. And the recall is calculated by the second formula, TP over TP plus FN, or instead, TP divided by the size of the target set, the pink circle. For example, when you execute a search expecting 10 documents, but the search engine returns only 3 documents that satisfy your expectation, the recall is 30%. Now we got evaluation measures, good. And in terms of these measures, we, as a user of a search engine, want a search engine that has high performance, one that the both precision and recall are high. However, it is impossible and is unable to be implemented. The problem is well known. There is a trade-off between precision and recall. It's that if you go after high precision, you get a search engine with low recall at the expense of it. Likewise, if you go after high recall, the search engine gives you high recall at the cost of precision. Why this happens? In order to implement a search engine with high recall, you need to adjust it so that it can produce a larger result set. Then, the result set covers almost entire target set. As you can see, it makes FN smaller, and you get high recall number. At the same time, you lose precision, because it makes FP bigger, and bigger FP makes your precision lower, and vice versa. When you want a search engine with high precision, you want the result set to be small. Consequently, you get not only high precision, but also low recall. That's the reason. Now, we understand why there is a trade-off between these measures. You can't have it both ways. But as a user, you want them both. How can you do that? NLP techniques can help you here. This is a solution for having it both ways that I have thought of. The important thing is to implement high recall first. But as a result, you got low precision, as I've showed you. To solve this problem, we have 2 methods. One of them is at the bottom left. It uses facet and filter query in order to gradually improve precision. The other method is at the bottom right. It uses the ranking tuning technique. Since ranking tuning is out of focus here, I want to focus on these other two boxes. In order to improve recall, there are several methods in Lucene and Solr, such as using n-gram instead of using morphological analyzer, using synonym dictionary. But here, I'll briefly introduce you to Transliteration as an NLP tool that may be used to improve recall. NLP4L has a tool for transliteration. I'll describe it later. Now we need to improve the decreased precision. To do that, we can use facet and filter queries. But these tools aren't always available. I'll explain the reason why in the next few slides. In order to make these techniques available, we can use named entity extraction. That is one of well-known NLP tasks. Document classification can be used for the same purpose, though I'll focus on named entity extraction in the later slides. Now, let's see how the facet and filter query can be used to improve the decreased precision. Imagine that you visit eBay website and search for a watch you want to buy when you don't have any particular watches in your mind. First, you would enter a keyword watch in the search box and click search button. Then you got many watches displayed on your screen. This blue circle is a set of watches you got. It should cover almost all watches you want to check. But if it stays as it is, you would have a hard time finding watches you like because you have so many unwanted watches in your result list. That's where the facet and filter query come in. You find facet links on the left of the screen. For example, there is a link to filter by gender, and you would click men's link. As it narrows down the search result, you get the smaller set. The other filter queries can be added. Again, you can click another link, for example, the link of 100 to 150 that appears in filter by price. Then you get further smaller result set. Now, the size of the result set is small enough and is easier to find watches you want to see. Now we see that the facet and filter query techniques can contribute to improving the decreased precision. To implement this scenario, documents that users will search must have a structure like this. The document needs to be structured. You see in this slide, the documents have price and gender field in order for filter query to be implemented. Unfortunately, not all documents in the world are structured. For example, articles in newspapers don't have the structure you see in this slide. So, one of NLP techniques can help you here. Named entity extractor is the answer to this. Named entities are distinguished by colors. NEE is a tool to find and extract named entities from articles. As each named entity belongs to its class or category, we can use NEE tool to convert our unstructured documents to structured documents. And eventually, we can apply facet and filter queries to them. NLP4L has an interface to OpenNLP to use NEE function. OpenNLP works nicely, but unfortunately, it doesn't have model files for Japanese. To implement them, we had tagged named entities for Japanese news articles by ourselves. To handle this task, we used BRAT, that is an open source software for text annotation. In total, we annotated several thousand of Japanese sentences. I'll explain about counting number of words in Lucene index. It looks trivial, but I think it's an important first step for NLP. This is a corpus which I will use to explain about counting words in the next few slides. We have 3 documents in our corpus. This is a Scala program that creates a Lucene index. The data source is here. We've seen this in the previous slide. This is the name of the Lucene index directory. This is a schema definition. It has only one field, text field. Standard tokenizer and lowercase filter are used in this field. This function creates a Lucene document object from a text. Open a writer here and use it to write documents, then close it. After running the code, we've got this Lucene index that serves our corpus in it. Now we can count the number of words. NLP4L provides various functions that count words in Lucene index. This is some total term flag, and it counts the words occurrence frequency in total in the field you specified. This is a method to count the number of unique terms in the specified field. This is total term flag, and it shows you the count of the word you specified in the specific field. There are other code snippets to get word count, top terms. There are 2 types sorting, sort by doc flag and total term flag. Let's get further into calculating probability. Because we've already know how to count the number of words in Lucene index, we can now calculate probabilities. Interestingly, I'll use Lucene's single filter to get probabilities. So, what is single filter? It's a word n-gram token filter. It is used in combination with a tokenizer because it is a token filter. This is a sample flow chart for it, where we use Lucene's white space tokenizer. And single filter follows this. We put this sentence, then white space tokenizer separates it into words. Single filter then produces word bigram series of tokens. We will use single filter later. Meanwhile, let's look at language model. Language model is often used to represent the fluency of language. For example, in machine translation, the translator uses language model in order to choose the most natural sentence from several candidates. This is a simple formula. It represents a conditional probability of word apple given that word an has occurred. Because an apple is more fluent than an chocolate, the probability of left side member is larger enough than the probability of right side member. As n-gram model is most widely used for calculating language model, let's see how we do it. It's simple. Here, to calculate the probability of word apple, given that word N has occurred. Result of counting the number of the series of an apple by the number of the word N. So, if we have a field that tokenizes word bigram and normal field, we can calculate language model from Lucene index. Now, let's see the code for language model. The code looks almost similar to what we've seen previously, except the schema. This is a schema. We have two fields, word and word2G. The word field is a normal field, whereas word2G is word bigram field. It uses single filter, and all text in the corpus is indexed. Then open the Lucene index in order to calculate probabilities of the language model. Then the same pattern can be used for part-of-speech tagging. We will use the same corpus again, but it has part-of-speech tags. And here, the table is a description. I'd like to use the Hidden Markov model to solve the part-of-speech tagging task. This is the formula for HMM. What we want to do is on left side. We have series of words here. These are given. Then we want to know the most likely series of part-of-speech tags. As it's difficult to solve this directly, by applying an approximation of HMM on the right side. We have two conditional probabilities here. And we can calculate these conditional probabilities by counting the number of words or even part-of-speech tags in Lucene index, as we've seen in the previous slide. And if we use our corpus for HMM training, we get this diagram. Numbers in this slide are probabilities. These probabilities can be calculated by applying the same method. Here is the code for HMM. We use tagged corpus here. We use HMM model index in order to create Lucene index that is used to calculate HMM. Now our corpus is indexed here. Then we get HMM model. And we get HMM tagger to solve part-of-speech tagging problem. Here we try to do post-tagging for the unknown sentence. Let's see an interesting application, transliteration, that NLP4L provides. Transliteration is a process of transcribing letters or words from one alphabet to another one to facilitate comprehension and pronunciation for non-native speakers. Here is an example of transliteration between English and Japanese. All Japanese words here originated from English words, so they are called loan words. Usually, Japanese loan words are written in katakana in order to simulate the pronunciation of original words. We Japanese often use English words in the document, but use katakana for queries or vice versa. Let's see a specific example. Here, the user searched an English word, mouse. But you got mouse in Japanese highlighted in search result. What we've learned here is that if we have a list of English katakana word pairs that are originated from English words, it helps improve recall for a search engine. That's nice. And what's nicer is that NLP4L has a training data for transliteration between English and Japanese. And in addition to that, transliteration program. NLP4L has this kind of training data that is a list of English-Japanese loanwords pairs. I've gathered them from the internet. Then I applied them for alignment. This aligned data can be used for training HMM. There is an example script in NLP4L for transliteration. Here it is. It can be executed by loading like this. This sample script learns the aligned data and creates a model. Throw in a katakana word, and the script predicts the most likely alphabetical word and returns it to you. This table represents the input katakana word and its predicted English word. As you would see, the returned strings are nothing more than prediction, so some of them are incorrect. That is, we cannot use them as they are in order to improve recall. So we need a solution. This is a solution for the problem. This is a system that crawls web pages on the internet to collect a pair of katakana and English alphabet strings. It assumes that the katakana word that is close to English words is a loan word of the English word. To make sure it's the loan word, it passes katakana word into transliteration program, then gets the predicted English word from transliteration program. Since the returned string is nothing more than a prediction, it may be correct or incorrect. But it should be similar to the real English word. Here, the edit distance comes into play. If the edit distance between the collected and predicted English words is less than a certain threshold, the program stores the collected pair of katakana and English words to the dictionary. This dictionary is called a synonym dictionary and can be used in Apache Solr in order to increase recall. I got more than 1,800 synonym records from Japanese Wikipedia. This concludes the introduction of current NLP4L tool. Though we have been providing consulting services using NLP4L, the number of customers we have a bit short of what we hoped for. And I should say the business is not quite successful. So we decided to provide a framework where various NLP4L tools can work on. NLP4L framework improves search experience of Lucene-based search systems such as Solr and Elasticsearch. We provide not only a framework, but also the tools which I introduced today as a reference implement. We are also planning to provide the transliteration corpus and learned NEE model files as well. We use NLP and machine learning technique to output models, dictionaries, and Lucene indexes. Because NLP and machine learning are not perfect, we provide a GUI that enables you to personally examine output dictionaries. This is an overview of framework. The blue frame is a framework, while the items inside it are functions provided as plugins. There also are several functions that I didn't have a chance to introduce to you today, or that we have not implemented as of yet. Moving forward, we will define blue arrow interfaces and provide implementation that conforms to that interfaces. NLP4L framework outputs data including word and phrase information that are extracted from sources, including corpus as search engine dictionaries. The output dictionaries are search word suggestion, did you mean search, synonym dictionary, user dictionary for morphological analyzer, and keyword attachment dictionary. In some cases, external machine learning tools, such as classification, are used. Because NLP and machine learning are not perfect, we provide a GUI that enables you to personally examine them. You can deploy these dictionaries to Solr and Elasticsearch from the GUI. Now, let me explain the keyword attachment dictionary. The keyword attachment dictionary is a dictionary that holds pair of document ID and the keyword list that you want to attach to that document as its items. You will refer to this dictionary when you are creating a Lucene index to attach any keywords to Lucene documents. You can then increase the boost value for that field. The keyword attachment is considered as a general implementation approach for functions including learning to rank, personalized search, named entity extraction, and document classification. Let's move on and let me explain learning to rank and personalized search. We usually use cosine similarity between query vector and each document vector. But there may be times we want to use learning to rank. Learning to rank is a task that machine learns data including access logs to obtain an appropriate search ranking. Please refer to learning to rank on Wikipedia for the detail. Let's think about realizing this with Lucene. Program learns from access log and other sources that the score of document D should be larger than the score that Lucene normally calculates for query Q. And as you can see in this diagram, it performs keyword attach query Q in the document D. Increasing the boost value of this field makes the ranking of this document go up from the next search. Personalized search means optimizing the search ranking for query Q on a searcher-by-searcher basis. Likewise, program learns from access log and other sources that the score of document D should be larger than the score that Lucene normally calculates for query Q by user U. Since you cannot pass U to the score function parameter, as Lucene restricts doing so, you have to combine query Q and the user U to create Q sub U. Now, this task can be realized by keyword attachment as well. But you have to devise ways such as limiting the data to high-order queries or dividing Lucene fields depending on users, because the number of query-user combination can be enormous. Okay, that's it. We are looking for engineers who are willing to work with us on NLP4L. Contact us if you are interested in our project and like the area, including information retrieval, NLP, and machine learning. Thank you.
Awesome. Thank you, Koji.